No, I was just going to do a single screen. No, I mean, I think the single screen is okay. Yeah, because I found the the projector system, it's kind of annoying to just write into the iPad. I don't. Yeah, I mean, if you, you can ask. Okay. I have in the past. Yeah, yeah, yeah. Okay, I think that we can. Will Igor or Aziz? Okay. And then, okay, yes, we can discuss some other stuff afterwards. Okay, so the motivation for this talk is that we had in the last talk the Aronson and Gottesman paper where we discussed improved simulation of stabilizer circuits. And so we start with a separate related question building off of this, which is what additional, so yes, what additional, let's call them resources, do we need to stabilizer circuits with for universal quantum computation? So that's the basic question. So let's just sort of begin by defining, so I will be using the notation of Bravyi and Kitaev, which is, so we let O be a set of operations. And we want to decompose this O in the following way. So we could say that we want O to be ideal and faulty. Or we can maybe better terminology that they don't use, but we have free operations and maybe costly operations. So building off of the Gottesman-Nil theorem, we can sort of assume that are ideal or free operations are those that we can efficiently simulate on a classical computer. So those could be stabilizer operations.
So these ideal correspond to free and also correspond to costly in some way?
Yes, exactly. That's exactly right. Yeah, so the ideal are the Clifford operations. These can be implemented fault tolerantly. And then the faulty ones will be these additional resources. It's going to be the magic states, which you start with some impure mixture. And then you, through the distillation algorithm that they have, you go from something that's faulty to being able to actually fault tolerantly implement one of these T gates. So stabilizer operations. So just so that we remember what that means, that's something like prepare an initial state 0. We could also have Clifford unitaries and measurements in the Pauli basis. So I think that I don't need to restate that the Gottesman-Mill theorem, which we talked about last time, basically says that quantum circuits involving precisely these elements can be simulated efficiently in a classical computer. So the second thing, so maybe I will just put it here, or it's okay. The faulty operations, that these will be the ability to prepare, so I will just write it out, prepare ancillary qubits in a mixed state. Okay, so let's just recall some preliminaries. And that is that we want to deal with, let's deal with a set of n qubits. So we have a Hilbert space that's something like this. And then we want to consider, we have the Pauli group, which, so also, okay, so just to make life a little bit easier, I will assume that we kind of know what the single qubit Pauli group is from last time. So the Pauli group on n qubits is sigma 1 all the way to sigma n, where each sigma I is an element of the single qubit Pauli group. And this takes account of the signs, because these can have plus or minus I, plus or minus 1, and x, y, and z in identity. Okay, and then so we also have the Clifford group on n qubits. So these are going to be generated by the Hadamard, the phase on each qubit, and then the controlled x, the controlled knot between any two qubits. And also, let's just finally, one last thing, is that we have the set of possible stabilizer Paulis. What do I mean by this? These are Pauli elements, such that these are Hermitians. So no plus or minus I coefficients. And so if we take, for example, we take some sigma 1 to sigma k element of this set here. Then, and we require that each of these commutes, then we have that a stabilizer group can be generated. This might not be an independent set, but something like this is a stabilizer group. Because these squared give you the identity, so the identity is in here, and so everything commutes. So this is one way to define the stabilizer group. Also, because they commute, we can define a set of joint eigenvalues for the outcomes.
Sorry, what is sigma n? There are sigmas in Gn, which is the Pauli group.
Yes, such that they're Hermitian.
Oh,
no plus or minus i's. So then when you don't have plus or minus i's, then yeah, if I just define some sort of commuting subset, then I have a stabilizer group.
They have plus minus one eigenvalue.
Yeah, exactly. So also, because this is a set of commuting Paulis, we can define a joint eigenspace for them. So let lambda vector be lambda 1 to lambda k, be the eigenvalues for each of the k generators, say. This can be, sorry, I don't need this. So this is a set. I can have this be R, or this one be R, sorry. Okay. They don't have to be the same, right? So, okay, I will keep this. So this is the set of eigenvalues for the generators of this. B, B, for the generators sigma 1 to sigma k. Then this is called a syndrome measurement, just because, so if I define the eigenvalues of these Paulis, and I can define a measurement that gives me these outcomes by specifying the projector. So pi is defined as, let's see, the product from I equals 1 to k of 1/2 I plus lambda I Si. Okay, so this is the projector onto the joint eigenspace of these Pauli generators. And we know that, we know that sigma, yes, sigma, sorry. I have a, sorry about that, yes. Perfect, thank you. Okay, I must have written that incorrectly. So just quickly, we can define the subspace that this pi, this projector projects onto the subspace. I will write it like this. This is the subspace that pi projects onto, and the dimension of this space is 2 to the n minus k.
But I think you assume that the sigma i's are independent generators, right?
Yes, that's right. These. Yes. So I take, this is a set of Hermitian Paulis, which could include the identity, and then this is the set of generators, which gives me, for instance, this set.
Generators, okay.
Yeah. Yeah. So that's why I changed the. This could be more R.
But the thing, so sigma 1 to sigma r, are you referring to all the elements of sigma n there, or?
All the elements of S. Yes, yeah.
All of them to commute for any sequence.
Yes,
Okay.
yeah. Okay, so let's see, that's just some preliminaries. Okay, so we want to return to this question of how do we recover universal quantum computation? So to this end, let's recall a couple of things for the single qubit case. So we have this block sphere representation. And so this is for a single qubit. So we have that single qubit, we have this, and we have that these density operators. So I won't define it. So, but these are positive semi-definite operators with trace 1. So then we can write any row element of can be written as something like rho equals 1/2 I plus x plus y. Sorry, this is got coefficients. Where these are the 2x2 Hermitian polymatrices. I will not write them out. I think that we've seen them before. So let's define this thing called a stabilizer polytope, which is an octahedron inside of the set of inside of the block sphere. So let's see if I will be able to draw. So how can I define this? Stabilizer is equal to the convex hull of stabilizer states. So I will just write this informally for a second. So what are the stabilizer states for a single qubit? For one qubit, we have that there are so it turns out that the only stabilizer states are the eigenstates of x, y, and z. So we have 6 potential vertices. We have 0, 1. We have plus, minus. This is for the z direction, the x direction, and this doesn't typically have a name, but I will call it up, down. This is for the y direction. So there's 6 vertices, and we want the convex hull. Sorry, one second. Yes, okay, that's okay. So we want the convex hull of these, and this turns out to be a octahedron. So if you write, for example, 0, 0 in terms of as an operator, this pure state will look something like 1/2 I plus x. So what are the coordinates of that? That's going to have rho has coordinates 1 for x and 0 for the other two. So we have basically 6 coordinates that are all 1s and 0s, plus or minus 1 and 0, 0. So this will be an octahedron. So we have for a single qubit, we have that the stabilizer polytope is equal to an octahedron. I think that it suffices to consider a picture. I will draw from looking down at the z-axis. We'll have something like the following. This is the block sphere. And we have something like this. So this is the x direction. y direction, and z is coming out of the page. This right here, sorry, this is the density, these are our quantum states, and everything that's inside of this square, of course this is an octahedron, this is just the profile of it, this is the stabilizer polytope. And so what basically you can rewrite the Gauss-Nil theorem as saying is that if we start from a product state where each of the where everything is coming from inside of the stabilizer polytope, then everything can be classically efficiently simulated. And then the question is, well, what if we start with products of states that are outside of this stabilizer polytope? Do we recover universal quantum computation? So the question becomes a little bit more precise. You see if our input state is, maybe I'll just say, not an element of stab, I don't know, something like this. Does that make sense? Okay, I mean, maybe it's a little too informal, but the basic idea is to say that we know that anything that's in the convex hull of this octahedron, if we start with some input state that's there and we can only perform Clifford unitaries and Pauli measurements, then according to Gauss-Nil, everything is efficiently classically simulatable. And then so it's like, okay, is there a sharp boundary between as soon as I leave this, is it the case that I recover universal quantum computation?
Also something like this tensor product is inside the stabilizers, right? For n qubits.
Yes.
You can ask a similar question for those outside.
Yes.
That's,
yeah.
They focus on this kind of like single.
Well, yes, we can focus on the single qubit case because, of course, there's the result that if you just have the Cliffords plus any, so that's, I'm inherently, so we can focus on the single qubit case because if you can prepare this single qubit operation that's not a Clifford, then that suffices. Okay, so I will leave this picture here. So let's talk about the magic states because there's a sort of, maybe I will just give a little preview. Geometrically, we'll consider two types of magic states. One will be these H states, which will be corresponding to if I take a point in the middle. So this is precisely in the middle of this octahedron, or the middle of the sphere, and I draw a line straight out to here. These will be my H states. And of course, there's a Clifford orbit, so this is one, and then if I act by the symmetries of the octahedron, I can generate more of these. So this is, look at the plane that cuts the origin, and then draw some lines radially outwards. These are the H states. It'll be harder to draw the T states from this perspective because what the T states are is you have the octahedron and the T states puncture precisely the face of the stabilizer. So let's see if I can. So if this is just, maybe that's not so obvious. Let me, 1 second. Okay, and this is something like this. Okay, just take this to be the top part of the stabilizer polytope. Then if you have a line going straight from here through the face of this, one of the faces of the octahedron, and then this is going to be your T state.
But these are kind of sometimes name them differently.
That's incredibly confusing. Yes. So no. So the ones that we want will be called the H state.
I didn't like to say the T gates.
No, yeah, the H state. So if you prepare an H state, then you can implement a T gate. But by the way, the T gate that they use in this paper is not the T gate. So we think of T equals the diagonal 1 e to the I pi over 4. This is they use a T gate in this paper, but it's not this. The T gate that they use is like up to some factors 1 I minus I or something. This is something like the Hadamard times the phase, or the other way around. Yeah, it makes it a little bit confusing to follow. Okay, so first let's just say what these, we want to look at certain operators. T in this case is e to the I pi over 4 times the phase gate times Hadamard, which is coming from the Hadamard, and then this is 1 I minus I. And then we also, just for completeness, we have the Hadamard, which is 1 minus 1. And then we define eigenstates of these operators. These are unitary operators, in fact, because you can see that they're also Clifford. So we have that T in H are eigenstates of TH respectively. Okay, and so we can be a little bit more explicit about this. So we have that T is equal to cosine alpha 0 plus e to the I pi over 4 sine alpha 1, where we define alpha by cosine 2 alpha equals 1 over the square root of 3. And also the H state equals cosine pi over, sorry, not pi over 4, pi over 8, 0 plus sine pi over 8, 1. So this is not in the common literature. I don't think that this is now how we define the H state. The relationship to what we normally think of as the H state, we will write as a pi over 4 is up to normalization plus e to the I pi over 4, 1. And this is like related to this one by, let's see if I have it here. It's related by oh yeah, so I can write it like this. Phase, Hadamard phase times A, phase, Hadamard phase times H equals A pi over 4. So, I mean, it's fine. It's all within the same Clifford orbit, just it's not the usual convention. Okay, where did I go? Okay, so I will not take the time to write this, but essentially I can take one of these T's or H's and I can apply any Clifford, any element of the Clifford group to it, and I call that state a T-type or an H-type magic state respectively. So there's not just one, but up to Clifford unitary. So let's see, is there anything that I want to use this picture for? No, okay, we're good. Okay, so we will there's this following result that I should write down. Okay, I could have used the picture. Maybe I can draw it again. 1 second. So the theorem is, so if we define the fidelity between a t state and a input state rho to be given as the max u element of the Clifford 1 t rho, u dagger rho u. So we define this to be the fidelity. We look for the max. Basically, you want to put rho into the same quadrant of the Bloch sphere as t is. And then the result is the following. Adaptive computation using O is equal to O ideal. Okay, so what is this saying? Adaptive computation using Clifford operations and an input state rho, which could be in principle noisy, allows universal quantum computation whenever we have that ft of rho is strictly greater than ft, which is defined to be the following value: 1/2 1 plus square root of 3 0.91, something like this. Okay, so this doesn't really mean too much, but there's the following remark. If there was, okay, so this is some threshold. So basically we have universal quantum computation anytime this fidelity ends up being greater than this number. If we could lower this number from 0.91, if we could have an improvement on this bound from ft to ft star, which is 0.888, what does this correspond to? This corresponds to the boundary of the octahedron. So if there was such a, if the bound was instead this, which I don't have the explicit expression here, it's like 1/2 1 plus 1 square root of 3.
Max on the stabilizer.
Yeah. So if the bound was this, basically it would be saying that there's a sharp boundary between which as soon as you leave the stabilizer polytope, you get universal quantum computation. Well, by this distillation algorithm, this is the lower bound. I think the paper that we're going to talk about next week, Reichart, improves on this. And I can't remember the punchline of that, whether presumably it's not this bound. Okay, so let's see how this works. Okay. So let's see how the simulation works. So let's define a phase shift operator equals 1, 0, 0, e to the I theta. And we consider, okay, and then we have the following theorem that we can use. And I found that this is attributed to Boykin et al., but I could be wrong about this being the first place, that Clifford plus phase shift are universal for quantum computation, so long as theta is not equal to a multiple of pi over 2. Sorry, an integer multiple probably. Okay, so let's kind of see how this works. Okay, so I will, in fact, so the following circuit is going to be useful.
Sorry, you say Q not equal.
Sorry, this is theta, right?
Sorry, theta not equal.
Yeah. So if theta is an integer multiple of pi over 2, then it's just a Clifford gate, right? Theta not, yes. Yes, thank you. So let's see how I want to approach this. Okay, so there's the case of theta equals pi over 4 is particularly nice because we can do an adaptive computation to always fix. So so this is why it's kind of very okay. So I will just do the general case first, and then we can look at this. Okay, so let's consider the following state equals 0 plus e to the I theta 1. So then what we want to do is actually, we want to think of how can we apply this phase gate without actually having this gate? Well, if we can prepare this kind of state, then, and also let psi be some arbitrary state, then what we will have accomplished our goal if we can apply this gate to this state. Okay, so maybe the following circuit will be useful. Okay, well, the following circuit works for pi over 4, so I will just do it like that. Doesn't work for any theta, for arbitrary theta, rather. So we have some C naught, which entangles them. And then if you perform a measurement in the computational basis of the second qubit, then actually, if this is pi over 4, you can fix this. Depending on the outcome here, you can perform the following unitary. Sorry, it should be, is it hx? Sorry, hold on, no. Px. And then you should get a theta acting on psi. And the outcome of this, say, is m here, or just x. And this state is just x. Okay. So, but you'll see when I do the computation out that you can't, for arbitrary theta, you can't always correct it. Say theta is equal to like pi over 6. Why does it work here? If it's pi over 4, what it turns out to be is that if I get 0, then I get precisely this. But if I get the outcome 1, I get a minus theta. And the way that you can correct a minus theta to a plus theta, if theta is equal to pi over 4, you can apply a phase gate, which flips you from minus pi over 4 to pi over 4. But if you have some other angle here, then it's not always the case that you have a Clifford that can fix this. Make sense? Yeah. Okay, so let's just work this out real quick. So say we have some input state, which is a tensor product of theta and psi. So we can write this whole thing out. This is an exercise in teleporting gates from BilQC plus alpha e to the I theta 1, 0 plus beta 0, 1 plus beta. Okay, so then we can apply the controlled X gate, and I will just skip a couple of steps. After I apply this gate, I can rewrite everything in a sort of nice way, which is alpha 0 plus e to the I theta. Sorry, there should be a beta here. 1 tensored with 0 on the second qubit plus, and there's maybe a factor here, e to the I theta. Oh, yeah, okay, beta e to the minus I theta 0 plus alpha 1. Okay, so now you kind of see what can happen. If I measure 0, I apply precisely the gate that I wish to have applied. If I get 1, however, on the second qubit, of course, then what happens is I get something that I have to sort of fix. And so there's 2 methods for fixing this. I already mentioned one of them. What time is it? Oh, sorry. Okay, it's good. So we require some sort of fix for this. One is that if theta equals pi over 4, then we can sort of fix this by, how do I fix this? I apply an x to switch the 0 and the 1, and then I apply a phase to go from minus I pi over 4 to the phase will apply plus pi over 2, so I get plus pi over 4. And so I can fix it just like this. So for theta equals pi over 2, there exists a Clifford which adaptively fixes to a pi over 4. Okay, so we can do this. The other suggestion, which is in the paper by Bravyi and Kitaev, is the following, that the outcomes on the second qubit, outcomes 0, 1, are random. And so if you have a supply, if there are k pairs of qubits that you can apply this procedure to, then you have a sort of random walk. Basically, you can just keep on applying this circuit until you can compute the probability that the random walk ends up on the positive plus theta. So let's see if I have this I can just write it like following. Sorry. So if you repeat this circuit repeatedly, you can have many possible circuits that you, many possible gates that you could have performed. So I'm just, p is some integer times theta, so p1, a, p2. And the pi's are random, follow random walk statistics. What am I trying to say here? Essentially that if you have this case, you have equal probability of getting 0 or 1 when you measure the second qubit. And so it's possible that you get it's possible that you get 1. So you want to compute the probability that if I have k such scenarios like this, what's the probability that within, or sorry, yes, if I prepare k such qubits and I measure all of them, what's the probability that within those k qubits, I always fail to get the 0? The 0 is the one that I want, right? Essentially, you have a sort of a random walk. Every time you have a qubit, you can try and get this 0 state. If it doesn't work, you apply the same thing again until you get the 0 state, and you can compute the probability that this whole scheme fails within k setups. Yeah, which is not that nice. So I think that this first approach is nicer. This is probably why people are using this this T state. In fact, yeah. So Bravyi and Kitaev do a lengthy sort of error analysis associated with the fact that in principle you can't correct for arbitrary theta in this way. So then you have to sort of do many trials, and you have to sort of figure out what's the probability of getting a success within some number of trials. And so I will sort of skip that part. Number 2. Okay, so now we can sort of go to the distillation algorithm. So what I'll do this time, next time I will consider, so there's two types of distillation algorithms, one for the T state and one for the H state. The T state is sort of more straightforward without a, if you don't have a certain background in certain kinds of quantum error correcting codes, which it's a little bit more straightforward to follow, although more brute force just computation. And then the distillation algorithm for the H is a little bit more elegant, but we'll talk about that next time in companion with the Reichart paper. Okay. Okay, so we want to consider, so the basic scheme is the following. Let's call this n to 1 is what the sort of basic lingo is. And the idea is that you're going to prepare n possible noisy ancilla states, rho, and through this, you're going to perform an operation where you prepare n of them, and then you perform a measurement. If the measurement comes up with a certain outcome, then you keep it. And if it doesn't, you discard it. And at the end of it, you should have a single qubit which can perform this logical sort of gate here. Okay, so we want to consider the T state, as you might suspect. And let's go back here. So we consider this T state, which can be written in this way as plus 1 over plus y plus z. So this is actually in the positive quadrant of the positive octant of the Bloch sphere. So what we want to do is actually consider, we want to prepare n copies of some ancilla single qubit state rho, where rho, I will just rewrite it, I plus rho x plus rho y plus rho z. And here, because this is in the first octant, we want to just restrict our attentions to density quantum states that are also in the first octant, the positive octant. So I will just take rho x, rho y, rho z greater than or equal to 0. In this way, the fidelity will be a maximum relative to t. Okay. So we define this following quantity, which is going to be 1 minus t rho t. This is called the initial error probability. And then we also define the output of our state will be a single qubit. So this is the initial error probability on each single qubit, ancilla qubit. And then we'll also have, okay, so maybe I should write it like this. Rho out will be, so this is a single qubit density matrix, will be the output of the scheme. And so we can define the error that we get on this, on the output, will be 1 minus t rho out t. And so what we want to understand is the following, that, or rather the result, I'll just give the punchline, and I will go through the steps momentarily. What we kind of want to understand is, as we prepare more ancilla qubits, what is the behavior of this E out? We want this E out to be small. So this is the initial error with which we prepare our ancilla qubits. And so this E out will be a function of the number of input qubits and this initial error probability. And we kind of want this thing to get to get better and better with larger n. So, okay, let's see, should I draw this? So as n goes to infinity, we have that there's an error threshold, E0, which equals 1/2 1 minus square root 3 over 7, 0.173. And basically the idea is that if E is greater than epsilon 0, then you get that E out converges to 0. And if E is less than, sorry, hold on, maybe it's the opposite. That makes less sense. Then we have that E out goes to the mixed state. the totally mixed or uniform state. Yes, this goes to 1/2, which corresponds to the mixed state. Yeah, but E out goes to 1/2, I guess. No, E out is this. No, yeah, that's right. That's why I'm correcting it. Yeah. No, you're right. So it's the value corresponding to what would become a mixed state. So just uniform. Just to give you an idea of what exactly that would mean, because it's not immediately obvious, I guess. Okay. Okay. So here is, here's the main idea here that we want to be able to go. We have the following distillation algorithm, which I will try to at least present a high-level view of it. You want to group qubits into 5-qubit blocks. This is sort of like the encoding part of a quantum error correcting code. You want to take in quantum error correction, you have some psi equals alpha 0 plus beta 1, and you encode it maybe in the 3-qubit error correcting code as something like 000 plus beta 111. So here we're going to, instead of just 3 qubits, there will be 5 qubits as part of the algorithm. So that's, and then we perform a syndrome measurement. I will define some Pauli operators in a second. You define some syndrome such that if the outcomes are all equal to +1, then this is a success, and you keep the resulting state. Else, you have that this is a failure, and you throw away that chunk of 5 qubits. N can be greater than 5. You basically fix some n, and then partition the n qubits into chunks of 5, and you're going to do the distillation algorithm on these 5-qubit chunks. And if you have that this outcome, this measurement is a failure, for that 5-qubit chunk, you throw it away.
So the measurement happens on the 5 qubits each time?
Yes. Okay, so now, so now we have to do a little bit of background stuff. Yeah, these are some facts that we need. So the T gate that I mentioned above has the following property. It has this cyclic property. T dagger equals Z. T dagger equals X. And T dagger equals Y. We also have that the eigenstates of this T, e to the I pi over 3 T0. And in fact, this T0 is just the T that I wrote before. And T1 is T1 equals e to the minus I pi over 3 T1. And in fact, I think that you can just correct. So T1 is related to T0 by YH T0 equals T1. So these are both T-type magic states, T0 and T1. So also, we are going to take our initial states rho. So they give an argument for how you can achieve this, but let's just take it as a given that our input state rho can be written as some error, some probability times T0 plus something like this. So then when we have our input state of 5 qubits, this is rho tensor 5. What is this going to look like? Well, this is just going to be a sum over. So I have all possible combinations here of T0s and 1s. Basically, I have a set of bit strings. So I have x element of Z2 to the 5. X 1 minus epsilon 5 minus x.
So this is the same epsilon, right?
Yes, so this is the same exact epsilon. This is the, yeah, so how do we understand this epsilon? This is the error initial error probability. So it's basically giving me the probability of an error. So here, if epsilon is equal to 0, then I get T0, which means that there's no error because T0 is the state that I want. Yeah. Exactly. So this is this one is the probability of my error because this is the one that I don't want. And so when I take the products of this, I have basically a bunch of T0s and T1s, all possible combinations of 5-bit strings. So I have something like this where I need to also x is the number of ones in the bit string. And also I have that Tx is basically a tensor product. Take the first element of the bit string, tensor it with Tx2. Okay, also introduce the following. We have the following Pauli's, which will be our, yes, in our stabilizer. So these are the generators, Z, Z, X, I. So I'm using the notation, this is on the first qubit, second, third, fourth, and fifth. S2, there's this cyclic property where I will now permute the I to the first qubit, X, Z, Z, X. And I will do this for, I guess I'm not saving too much time by doing this, but ZX, sorry, I, Z, X, I, X, Z. Something like this. And actually, I will just write the third one for completeness. Might as well. So X, I, X, Z, Z. So you can see that there's a cyclic property here. In fact, if I look at the full stabilizer group, I have basically all possible products that contain, so if I, for example, multiply these two together, what am I going to get? I'm going to get x up to some overall constant, x times y times I times y times x. So I get this same, what does the stabilizer group consist of? Paulis that have this symmetry, but with the x, z's, and y's all replaced.
fourth location? Do you multiply them all? Do you get an identity?
If I multiply all 4 of these, I get the 5th permutation of this. Yeah, yeah. So S5, it's a S1, S2, S3, S4. Yeah, it gives me the identity in this last location. And so let's also there's the projector onto this eigenspace. So we want to consider the all plus 1 eigenspace. So we have that this projector is 1 over 16. I equals 1 to 4. I plus Si, which is why I think I made the mistake before. And the subspace that this projects onto, L, which is equal to, I'll write it like this. This is a 2-dimensional subspace. 2 to the 5 minus 4. And so this is like we are looking at an error correction code for encoding a single qubit. Okay, so I can probably anyway. We can also define some logical x, y, and z. This is x tensor to the 5. Sorry, y tensor to the 5. Z hat equals z tensor to the 5, and so these are logical x, y, and z and t in the sense that they obey the same exact algebraic expressions as the single qubit versions of these. Because it's an odd number, you sort of get precisely the right coefficients in front. And then, let's see, what do I want to say about this? So these commute with SIs, so that's something that I was going to say. In fact, this does not commute with the SIs, but what they all do is they commute with pi. Why? So what does T do? T permutes x to y, or sorry, x to z, z to y. So, but what it does do, the action of T on the stabilizer produces other polys that are inside the stabilizer group. So it fixes the projector, but it doesn't fix. Yeah. Okay, so we have that pi comma, I will call this g equals 0, g okay, so you can show this, it's not so bad. Okay. And sorry. Okay, so without taking too much time, what's the basic idea that we want to get a hold of here? Do I have time? I have 20 minutes. Okay. So here's what we want to do. Essentially, what we would like is to have a final row. So we will perform a measurement. So I'm just going to sort of see if I can outline the argument. So I can have a final row, which is the output of a successful syndrome measurement, which will be pi row in pi. And it will be an expression using the epsilons and stuff. So I'm not going to write it all out. And what we want is the probability of that measurement, which is going to be trace of row S. So this is the probability of getting this precisely this outcome, which is the one that we want. And so now we have to go ahead and compute this thing. So it's basically just algebra. I don't know if there's a good point in going through it. Is this something that you'd like to see? It's not particularly illuminating, so I think that what it turns out to be is that for the H distillation, this is just sort of brute force calculation at this point. I take this pi and I apply it to this row S, and at the end of it, if I get this successful sort of, if I get this state right here, what I can do is, once I get this state, what I can possibly do is decode this using a V. So then there exists a V element of the Clifford on 5 qubits, which takes me from this output such that it takes me from this output to something like the following. Takes me such that, yes, V L equals C squared tensor. Okay, if I get this, what can I do? I can apply a Clifford unitary that puts all of these S's into a canonical form where they're all just Z's. And so I will have something that's some arbitrary 1 qubit state times zeros. And this 1 qubit state will be precisely the logical T state that I want to apply. So now what's on the first qubit will be something like the T state that when I measure on, this is the T state precisely that I want to measure. Or sorry, yeah. Yeah, so this was just to get a final, basically I go from a set of 5 noisy inputs, I perform this measurement. If it's successful, I keep this set of 5 qubits. I can perform a decoding that brings me to something like this. And then this is precisely the state that enters into the circuit that we want. So that's kind of the procedure. I did skip over a lot of the algebra, which it will make this more complete, maybe in your head, but it's not like it's not very illuminating, I don't think.
If you say, let's say, 10 of those, then you just apply this procedure to each 5.
Yes, each 5. I have 2.
Then you don't do anything, right? Because it's not like 5 qubits.
No, I throw these away, right?
These are gone, but at the end you ended up with 2 qubits, right?
Yeah, I have precisely 2 that encode the state that I want.
Oh, I see. I thought, like, let's say you have 5 times 5, then you would end up 5 states, and you don't iterate it again, right? You just stop there when you get this 5 qubit state after 25 or 25 qubit state. So you just apply this once, like to each 5 blocks.
Yes.
And then you get, I don't know, if you have n qubits, you have something like n over 5.
Yes, roughly. Yeah, with some probability, exactly. Okay. Yes, so I mean, this is the distillation part of it, yes. So I think next time I will talk about the H-type distillation and also do this Reichardt's paper, who improves on some of these bounds. Okay. Let's see if there's any.
Okay, so maybe there are questions there?
No, doesn't seem to be the case. Any questions?
Okay, otherwise,
Okay.
thank you for the talk.
Okay, sounds good. Let's end the recording.